expected to start. So yes, so Bruno is a big shot in the control community, we know, and he is one of the few in our community that really made high impact contribution to resilient cyber-physical systems. So it's my great honor and privilege today to welcome Bruno for this graduate school. So Bruno Sinopoli is the Das Family Distinguished Professor at Washington University in St. Louis, where he is also the founding director of the Center for Trustworthy AI in Cyber-Physical Systems. And also he chairs the Electrical and System Engineering Department. So this is also why I would like to thank you again, Bruno, for you are head of department, but still you agreed to provide this lecture here. We are very happy and proud about that. And maybe I should, just say that you were, you got your PhD from Berkeley, and you had postdoctoral position at Stanford, and you were at Carnegie Mellon, and now you are at University of Washington, St. Louis. And maybe, okay, if I start saying all your awards and all these things, we probably finish in 3 hours. So maybe I should stop here. And I really would like to welcome you, and thanks again for providing this 2 days lecture. Thanks, Bruno.
Thank you, Thomas, and thank you all organizers of this workshop for inviting me. It is a privilege for me, Thomas, to be here, regardless of our administrative duties. And Thomas, you have your share of that, and just let me thank you for your leadership of the Control Systems Society. It's a thankless job. Anybody who has done administration, I think Chris Agikosi is also here. He also knows as a chair or former chair. I don't know, Chris, if you're still the chair of the department there. It takes a lot of commitment and selflessness, if that's a word, to do this. Nonetheless, our heart is always in the science and in the engineering. So I'm always happy to be able to talk about science and engineering. So with that said, I would like to proceed, given that we started. But before, I would like to question, the issue with units is something that created a lot of troubles in the past, right? The most famous, not most famous, but probably one of the most recent is one of the Mars missions, right? I don't know if anybody remembers what happened. Does anybody know what happened in one of the Mars missions? One of the first, I think, Mars missions. Why? One of the reasons it failed. Okay, so I want to know whether people are shy, or because I don't want to talk for 3 hours here. So I'm going to try to instigate people to say things. But it was poor system integration, right? When you build very complex systems, right, and cyber-physical systems that we will talk about today are complex systems. What the strategy in engineering is called divide and conquer, right? And so you basically separate the task. You have different teams working on different tasks, and then you bring the tasks together. And when you do that, you have to be careful, right? First of all, you're usually suboptimal when you do that, right? Because you're not doing work at the intersection of domains, right? So you are not exploiting the dependencies, right? And even worse, you have to make sure that when you integrate the properties like safety and reliability are satisfied, right? And so when they did that, this Mars mission, there was one module which was developed by a company that was working with the imperial system, right? With feet, gallons, fluid ounces, and whatnot. There was a company that was working thankfully, with the metric system. This is an uphill battle that I've been fighting here in the US since I arrived against the imperial system. It's a lost battle, as you can see. And therefore, when they put the two modules together, the numbers did not work. And the rover mission failed, okay? So as you can see, Thomas, there are worse consequences of a little misunderstanding. This is not too bad after all. Okay, so with that premise, let me try to share my screen and let me make sure that everybody can see.
That's great. That's great, Bruno. That's great.
Okay, all right. But this doesn't work now, so I'm going to stop sharing and share again. Here's an issue with PowerPoint. Now everything is working. All right. So so first of all, let me take a little poll, and so just to understand a little bit the audience, right? How many of you are, and what you can do is just raise your thumb in Zoom. By now, in this 1.5 years of agony with COVID, you are experts with Zoom. Are PhD students? Just raise your thumb if you can. Is it enabled? Yeah, it is enabled. Or your hand, doesn't matter. Yeah. Okay. Just a few. How many are postdocs, system scientists, and the likes? Okay. And then they have a few faculty, I believe. Okay. And how many are not from the field of systems and control? Okay, this is a more important question, I guess. Okay. We have a few. So, okay. So for this few, I will try to, because the set of lecture is really geared toward people who have some knowledge of system theory, but I will try to make it accessible to everyone. Okay. All right. First of all, let me acknowledge students and postdocs. These are the people who have mostly contributed to the work that I'm presenting today, and many collaborators that have worked with me around the world these few years. So before, let me give you a historical perspective, which is a personal one, right? When we studied, right, math was the king and the queen, the king and the queen, and at that time, beautiful theories and formalisms were developed in somewhat in an independent manner, right? And so we have a contribution in system theory, communication theory, linear algebra, and computation, right? So by a number of eminent minds, and can you identify a few of them? Aside so you should all know, if you're in control, at least the first two on the top left. Okay, Turing is in the bottom from the left bottom third, 3. And anybody else? Shannon, okay, good. Shannon is just right above Turing. For Neumann, very good. Who else? Let's see, the cartoons are, that should tell you that, pictures were not. Bodhi and Kalman, good for the controller. Good, Alexander. So top left, Bodhi and Kalman. And then there's Boole, Babbage. And I actually made a mistake on one of them because I just cannot find the picture of Witzenhausen I wanted to put there, but I just don't have a picture. So the picture that is there is not a thing. Okay. Very good. So people made connections, right? As early, very early, right? Wiener, in his famous book on cybernetics, talks about the connections between communication and automatic control systems in both machine and living things, right? Witzenhausen, a few years later, talks about in control, in a famous article on separation of estimation and control. He defines this this notion of information patterns, right? Who knows what and when, right? And depending on who knows what and when, then you can give a pretty good definition and of distributed and centralized control through the definition of classical and non-classical information patterns, right? Where classical is the beautiful one that allows us to do all the separation of estimation control, and non-classical is the one that makes things messy, right? Systems also, very complex systems, were built without the notion of CPS, right? We sent people to the moon with actually very, I mean, compared to today, primordial technology, nonetheless. How was this done, right? How did we send people? Mostly, we used what we call separation of concerns, which I alluded to before when I talked about divide and conquer, right? This is divide and conquer by separating the different domains, right? If you look at this, this is a classical example of a control system that you will find in your labs, which is called, it's an inverted pendulum, right? So how were control systems designed, right, before, right? You had, if you see, there's the plant, which is the inverted pendulum, and then you had a wire, which is probably some sort of a serial port for communication, and then you had a computer, right? And the key observation here is that the computer and the communication were dedicated to satisfy the task at hand, right? So you had control over that. And so as long as you design your communication and your computing such that the sum of the two were less of the sampling period that you had picked for the system, then you were in business. You could completely abstract away the computation, the communication, because you did not care. It satisfied the specification that you had provided, and your system will work as your equations had predicted. Okay. And also systems were designed with great investments, right? If you go back to the Apollo program, it employed about 400,000 people and required the support of over 20,000 industrial firms and universities. It's a massive endeavor, right? Which was rendered available only through a lot of funding. Okay, so for that reason, so disciplines stayed separated for quite a while, right? And one consequence of that each developed its own language and its own formalism, right? Which were quite different from each other. Okay, so now these days we talk about large-scale systems, which are not which are much larger than the Apollo, right? Because it's made not just of one system trying to compute a task, but of very largely distributed systems, right? Which are composed of thousands, tens of thousands, and sometimes millions of agents, whereby agents are actors, are actuators, which have their own intelligence, right? And also very difficult to model, right? These are the applications of today, right? We all talk about smart buildings. Transportation systems is a very hot topic because of the push toward autonomous transportation, right? And while we have fairly reliable autonomous cars, the issue is what happens when we start putting thousands of them on the road together, or millions on the road together or alongside with human drivers, right? How are they going to behave? Same thing with manufacturing and the smart grid, especially with integration of renewables, demand response. Okay, there's a technology push at the same time. There is widespread availability of networking, wireless, ubiquitous computing, right? And which is made of off-the-shelf hardware and software, right? Talking Wi-Fi, we're talking Bluetooth, right? We're talking LTE, right? And computers just general purpose computing, as well as microcontrollers and so on and so forth, right? One of the consequences of this technology push is that you don't have the luxury anymore of having dedicated computing and communication, right? Because, right, if you're doing smart buildings, for instance, right, you're going to use off-the-shelf technology to control a building. So you're going to use the Wi-Fi that has been developed that is present, right, and which is a off-the-shelf technology, which might be and will be in most cases shared with a number of other applications, right? You do your email and the likes, right? So and this is to abate cost, right? It is unconceivable for this application to use dedicated technology. Just the cost would be too high, and they would easily trump the benefits of actually trying to control them. The other consequence is that you don't have any more air gaps. An air gap is referred to as a way of protecting system by isolating them. Right? Systems are now connected, and they're connected over the internet. Okay, so things become much less clean than before, because domains intersect now, right? And you have to work at the intersection of such domains, right? And that's where the cyber-physical systems took place. We had cyber-physical systems much before the name was invented. You can argue that a digital controller is already a cyber-physical system, as the one we saw with the inverted pendulum, and it's true, is the way we approach them. There is the approach, the design of such system, which is different. Okay, so we're really trying to combine the physical space with the cyberspace. And when we do that, we do co-design, right? And by doing co-design, we necessarily have to bring together control, communication, computing, right? And that's a major challenge, right? Because systems, right, and networking and cyber components, we have to bring them together in one way or another. So at the beginning of the century of the millennium, I can say that, right, people started looking at combining control with communication and networking, right? And so this field of network control system, which existed again before, it's not that people never thought about these things, right? But when a big portion of size of the community start working on the same problem, then that's when you make the major leaps. And so when this critical mass was achieved, people started looking at how to do co-design of communication and control, right? Things, nothing new, things that Hans Witzenhausen had thought about 30 years before, that Wiener had conceived even longer than that, right? So how do you model such cyber-physical system? Right? If you take smart grid autonomous transportation system and you try to build a accurate a model of it, then you're going to be probably overwhelmed because it will be very difficult to build models where you can do any analysis. So I think the right approach is to start simple, try to derive some fundamental properties, right, of systems in this scenario, and so that then you can provide some design guidelines, again, some fundamental limitation of what cannot be achieved, right? And then slowly moving toward the technology transition by elaborating on models or trying to use this very abstract result to drive the design of engineering. Okay. Another thing that, and here we actually can discuss, right? Right. In control, we had this notion of stability, right? Which has existed in the centuries, right? From Torricelli through Lagrange and others, until it was beautifully codified in mathematical terms by Lyapunov in the late 1800s. Right? And so I claim that talking about CPS, the main goal is to preserve safe operations. It's slightly different from trying to enforce stability, right? And in its simplest way, the notion of safety is keeping the state of the system, right? And for the non-control people, if you have a car, you can think about the state as position and velocity, right? Within a so-called safe set, right? If you're going down the highway, you want to make sure that the safe set is staying within the road, or on your side of the road, within your lane, and keeping a certain distance from other vehicles. Okay. Why I don't think that asymptotic or Lyapunov stability is still that relevant, right? If you look at Lyapunov stability, basically says that if you establish some bounds on your trajectory, which is this epsilon, right? It says there always exist initial conditions such that your trajectory will stay within these bounds epsilon, right? As long as you start in the circle or in the ball of radius delta, stay within epsilon, right? These are very stringent requirements, right? What happens if trajectories occasionally exit the epsilon ball? Is that a big problem? I mean, for stability, yes, but probably is not a big issue as long as the set of states that are reached are still safe. Okay, so so in our analysis, in my opinion at least, and this is debatable, should really target the concept of safety, right? And there's a lot of research in the community that now looks at this concept, which is difficult to achieve for large-scale systems. Also computationally, it's pretty hard, and things are rendered more complicated by the advent and the use of data-driven methods, such as reinforcement learning, where the absence of a model makes it even more difficult to compute what is safe and what is not safe and predict whether actions in the future will keep the system safe. Okay, another thing that I would like to highlight is the notion of robustness and resilience. In the past, I have just used the two terms interchangeably, and I apologize for that. Right? I think by thinking a little more deeply, I believe that there's a difference between robustness and resilience. And again, since these two concepts are really not defined precisely mathematically, this is again debatable. To me, the notion of robustness is the ability of the system to withstand perturbation without the need for adaptation. Right? So you design your system, you predict that there are going to be disturbances, you design taking into account the disturbances might occur, right? And then you just let the system run, right? What is beautiful about this is that you design the system once and you don't need to adapt, right? One of the issues is that it usually robustness and I'm preaching to the choir here, usually leads to conservative design solutions, and therefore you pay with reduced performance because you have to be more conservative, because you have to take into account all possible disturbances that can occur, right? Whether they occur or not. Okay. Resilience, in my mind, is the ability of the system to respond to perturbation, right, and restore a certain level of functionality, which could be lower than the initial one, which could be equal, or even when disruptions occur, you might be able to redesign the system to achieve a higher level of functionality, right? So, so some of the advantages is the ability to restore full functionality or even better, right? And you can then be less conservative in design, right? Because when something occurs, then you're able to adapt, right? The disadvantage, in my mind, is the added complexity to the system. You can imagine why, right? Right. You have to add all sorts of different modules to the system, right? And if there's a perturbation, a disruption, you have to detect that there's a perturbation. You have to identify its perturbation, and then you have to redesign, right? First of all, yeah, redesign. Okay. Among this set of disruption, one of the major ones, and we keep seeing examples popping up, right, is the one of security, right? There were a number of examples in the early 2000s, right? The Marucci incident, but I think the very first one that made people aware of the issue of security in physical systems was a Stuxnet, right? And while I'm sure all of you know about Stuxnet, let me tell you a little bit about it. Right? Stuxnet was a malware allegedly planted by secret services of Israel and the US, and I say again, allegedly, right? Nothing has been proved. Where they targeted some uranium enrichment facilities in Iran. Right? The way this was architected was very clever, and it was delivered via some USB keys. But in order not to burn the advantage, the malware was designed to activate itself only when the target was reached. So, so it was probably in a number of computers before, but did not reveal itself. Had it done that, probably they would have found a fix, and then when it finally had arrived at the destination, it would not work. This way, it didn't. So it targeted some Siemens equipment for SCADA, right, which activated when it reached this uranium enrichment, right? And what it did was very clever. So it recorded the operation of this enrichment facilities, and the way this, I'm going to make it very simple, although it's probably not, right? The way you enrich uranium, there are these centrifuges, and you spin them at a certain speed, and the process then occurs. I don't know how, and it's probably irrelevant, right? And so what they did, they recorded what these velocities were, and then what they did, they took control of the master SCADA computer, which was receiving all the sensor readings, and they corrupted the sensor readings, right, by showing to the operator or to any detection scheme that failure detection scheme that was there, that that the speed that the centrifuges were spinning at was the prescribed one. Instead, they were spinning the centrifuges very widely out of control by changing the speed and the direction of it. And since these are very delicate mechanisms, they broke a number of them, so delaying the Iranian nuclear program. Right, this was a very very famous example of security in security breach in the physical systems for defense purposes, or whatever you might call it. Right? There's situations of ransomware. This is very recent, right? This is taken from a CNN report of Wednesday, May 19, 2021, where the Colonial pipeline was hijacked, and a payment was requested so as to resume operation. Right. Earlier than that, another very interesting hack was the one of a Jeep vehicle. And this was perpetrated by, it was a benign thing, it was perpetrated by two scientists, as a matter of fact, who wirelessly took control of a Jeep and just moved it, managed to control it by accessing the ECU through the entertainment system. So just to complete the story, what they did, they showed Fiat Chrysler what they had done, and they did not release the hack until Fiat Chrysler had provided a fix for it. So a few months later. But I was surprised that one of the two hackers came to talk when I was back at Carnegie Mellon, and I was surprised. Actually, I was not surprised to see that I remember, was it Uber or Tesla had hired them, which tells you how sometimes automotive companies are not very ready to react, like more of the Silicon Valley companies. Right? If I was Fiat Chrysler, I would have hired these people right away. And then other issues, other famous issues were the Ukraine power system attacks, and since then there probably have been more. Okay, this is just to motivate that this is a serious issue, and so the reasons, there's a lot of motivations, right? Why this would happen. There's cyber warfare, right? Disrupt key infrastructure, which was the example with the Stuxnet, right? Commercial advantage, right? You want to learn how a competitor is doing things, right? Perhaps you can launch a stealthy attack in its operations. By stealthy means an attack that cannot be detected or easily detected. And so you can reduce their performance and you gain a competitive edge. Or ransomware, right? Which, like the Colonial pipeline, right? And attacking physical system to a certain extent is easier, right? Because CPS are composed of various heterogeneous systems and components, and often they are distributed in the field, right? Think about power systems. There's lots of components which have intelligence that you cannot protect physically, right? Because it just costs too much. They're easily accessible, right? Also, CPS are increasingly connected and they can be accessed via the internet. Many companies, if you take smart grids, right? These days, the operation, the SCADA operation is connected to the business operations, right? Which runs over the internet. And so it's conceivable that you can enter through the business portion of the system into the operational one. And SCADA system these days use Ethernet, right? And you know, there were examples where you would see operators having the password stuck to the computer with a post-it or written somewhere, right? Or even worse, right, when you get delivered some physical component, it comes with some default password or PIN, which is usually the 1234, which everybody knows, and they're easily hackable, right? I mean, I don't want to blame the SCADA operators, right? Sometimes, actually, often these systems are safety critical. And there's nothing worse than forgetting your password when you have to access the system very quickly to prevent some damage. So I can understand why they would do that. The other major problem is with these large systems, which are large organizations, is the insider threat, right? You have an insider who has already gained access to the system, can corrupt pretty easily, right, by offering some maybe monetary incentive. And this is a very heinous attack because it basically overcomes and skips any access control that there might be. All right. So in terms of challenges, right, protecting cyber-physical systems poses new challenges, right? Physical systems usually have inertia. Right? And when a system has inertia, you don't have the luxury of bringing it to a halt immediately, right? If you have a computer and you realize it's compromised, it takes as little as unplugging it to turn it off, right? If it's an airplane that is flying, you cannot do the same, right? First of all, when you realize that you're under attack, you have to continue operating under attack, right? We have what we call graceful degradation, right? Ideally, what you would want to do is preserve the key functionalities of a system, right? While giving up the ones that are not crucial to safety. There are cultural issues in the protecting physical systems. I'm going to not discuss those. And also patches in the physical world might be more expensive, right? Think about the Jeep Chrysler. The recall of thousands or tens of thousands of vehicles is incredibly costly, and it takes also time, which allows an attacker to operate undisturbed while patches are applied. Okay. But not all the world is gray. I think that there are important opportunities that cyber physical systems have that traditional cyber systems do not. Right? Physical systems follow physical laws, and therefore, and there are models for these physical laws, right? And so it's easier to a certain extent to build accurate models of physical systems than of purely cyber systems, right? And we can use the predictive power of these models to try to predict future behavior, right? And by doing so, we have the predicted behavior. We have also sensor data, right, that tells you what the actual behavior is. We can compare, right? When we start comparing, there's a whole literature, and here we have some eminent representatives of fault detection, fault tolerant theory, right? You can start comparing, and then you can tell whether the expected behavior is matched by the actual behavior. Right? Then you can build monitors, passive, active monitors, right? You can use the physics also of the system to authenticate the cyber system, which to me is an incredible opportunity, because corrupting cyber systems is not fairly easy, but it can be done remotely. But while corrupting the physics of the system is something that is way more challenging, because you have to have access to the system, right? Also, the mathematics, if you have models, mathematical models of the system, then you might be able to prove security properties, and you can prove security properties that might work for classes of system, right? One of the issues with security is that given a system, you have to find ad hoc methodologies to protect them, right? If you have models and general models, then you can work with those and therefore provide countermeasures that are more general and work for class of systems, and that provides lots of advantages, as you can imagine. Okay, so this is the vision that I have for CPS resilience. So first of all, you have to design the system not just for performance, but also for security. This is a major issue, not technologically speaking, but commercially, right? Because when you design a system for performance and for and security, what happens is, silence my phone. What happens is that cost rises, right? So and selling security upfront is a major challenge, and to me is one of the reasons why security is always introduced as an afterthought, right? You design the system for performance, people buy performance, and then security issues arise, and then you start patching them. And for physical system, using this strategy, I think, is deleterious and very dangerous, right? Because when you deal with physical systems, you deal with people's lives, and so that requires a lot more attention. The next step is that the detection, right? You have to understand whether some anomaly is present, right? And you can do it in a number of ways, right? I'll show us how to leverage system knowledge to recognize that an attack has occurred. And then you want to isolate, identify the faulty components, and you have two types of responses, right? One is time triggered, right? Once you realize something has occurred, you put prevention mechanism to guarantee this security, and also detection triggered responses, right? Where in response to a certain detection, you put in place mechanisms to guarantee security and performance, right? The first case, you don't really need detection. You do it periodically, but you lose the definite performance. In the second case, it's really a response. Okay, and so I'm going to tell you a little bit about this in this couple of days that we're together. Okay. If you have questions, just stop me at any time, and we can have a chat. So I was thinking of having a couple of breaks. Given that we started a little late, maybe we'll have a break in a few minutes, and then one in an hour later, 10 minutes break where we can chat, or you can just stretch your legs. Okay, so important to the definition of, right, to set up the problem properly is to identify the capabilities of the attacker, right? And this is a process which is qualitative in nature at the beginning, and then you can make it more quantitative. Okay, and this is a characterization that I particularly liked. It was done by Andre and Kalle and other people at KTH. But basically, they put, and again, this is qualitative, right? The attacker capabilities on a 3D graph, right? Which shows system knowledge, disclosure resources, and disruption resources, right? So system knowledge is, what do I know about the system? Right? Disclosure resources is more of real time. What kind of real time information can I gain about the system, right? Can I, for instance, corrupt sensor measurements? Can I gain access to the inputs that are going into the system? And for instance, a eavesdropping attack is the one that targets these disclosure resources, right? And then there is disruption resources, which can I corrupt the system or the data in such a way, right? So there are topology attacks where I work directly. It could be a physical attack on the topology of the system, therefore on the plant, right? There could be denial of service attacks where I prevent communication from occurring, right? Or integrity attack where I am corrupting the integrity of sensor readings and of, for instance, of inputs, or even the algorithm themselves, right? And once you do that, you can start populating this graph by putting all the different attacks on this graph. And again, this is qualitative, but it provides a way of somehow ordering this type of attacks. And these are all attacks that have been studied in the literature. there's a fairly vast literature that's been developed in the last 10 years or so, right? And even beyond what I was able or I'm able to track, and therefore let me make a disclosure. This is just these are just initial thoughts. I mean, and the results that that I show you here might have been, hopefully they have been superseded or generalized by other people in the community, right? So I suggest that you take a very broad look at what has been done. Okay, so one thing that I would like you to notice, right, is to a certain extent, the farthest you are from the origin, the strongest is the attack, right? Qualitatively speaking, right? Where the strongest attack you can consider to be this covert attack, right? Covert attack is a particularly heinous type of attack where basically the attacker has full system knowledge, full disclosure resources, and full disruption resources. And Roy Smith, in a paper a few years ago, showed that in this case, there is nothing that you can do really, right? If an attacker is so powerful to have a full system knowledge, disclosure resource, and disruption resources, then it can drive the system wherever it wants without letting the system operator be able to detect, right? Basically, we'll do so by driving or controlling the system, but showing to the operator, to any algorithms attempting to detect such an attack, a view of the system which is compatible with the inputs that the controller provided and the system. Okay, so there's nothing that you can do. So to a certain extent, you want to find countermeasure or detection methods that approach this covert attack, right? The more resources you give to the attacker, right, and the more difficult it is to detect. But once you have found a detection scheme that works for it, then it works for all the lesser attack or the weaker type of attacks. Okay, an important observation. All right. Cannot find. Okay. Okay. Clear. Interesting. Okay. Any question? And I don't know whether the audio is enabled, but you just feel free to speak, to put it in the chat, whatever you're comfortable with. Okay. Not, let me proceed more with attacker strategies. So confidentiality can be, for instance, compromised by eavesdropping attack, availability, right, by denial of service attack, and integrity. Remember, these are the three properties of security, right? Confidentiality, availability, and integrity, right? It's broader now, right? Because it's not just the information, because there's a physical system. Right? And you can compromise integrity via topology attacks, where you change the system, and integrity attacks by a number of them. And we'll cover a few of those in this course. Okay, let me focus now on integrity attacks. Integrity attacks can be both, they can be performed both the cyber and the physical realm. right? Kind of trivial in the cyber realm, right? You intercept a packet and you either substitute it or you can corrupt it. And if you have a sensor reading, then you can modify that sensor reading so that the estimator, the non-control people, the estimator is just an algorithm that takes the sensor reading and try to estimate the state of the plant, right? And the controller, which is one that designs a control input on the task, right, may do their designs based on faulty or bad measurements. And the other thing that you can do once the control input is sent to the actuators, if you're able to intercept that channel as well, then you can modify the control input, right? And so you modify the control input because you want the plant to go to a state or to an operating point that that the attacker desires, right? And you usually corrupt the sensor measurements so that this disruption is not visible. Okay. In the physical realm, right, attacks can be perpetrated directly on the actuators or the sensors, right? They're very simple attacks that you can do where you don't even need to access the sensor. Think about, and this is a trivial academic example, I understand that, but it just gives you an idea. You're trying to corrupt temperature control in the room you're in, right? A physical sensor integrity attack is to corrupt the environmental condition around this sensor, right? The sensor can only capture temperature, for instance, next to itself, right? If you can corrupt the temperature near it, then you have achieved your goal because the sensor is going to send measurements which are not telling of the actual situation of the room. Okay. Okay, so in mathematical terms, if you're using a linear system for the non-control people, right? X is just the state of the system. If it's a car, it's positions and velocity in 2D, right? And position, velocity, and maybe heading, right? A direction of the A is a matrix that indicates the inertia of the system, right? U are the inputs, right, which go through B, which models the actuation, right? And W is some noise that tries to characterize the inaccuracies of the model, right? And as you can see here, integrity attack will corrupt the UK that has been designed by the controller by modifying some of the components of this U, right? This gamma U is a matrix, indicates which components, right, are compromised. You can think of it as a diagonal matrix that has ones in correspondence of the inputs that get compromised. The same thing happens in the second equation. The second equation is called the observation equation. And Y are just the outputs. Let's say when you have a car, you can measure velocity, for instance, right? So a linear function of the state, which can be corrupted by an attacker in the same way that the input is corrupted, right? While VK is sensor noise, capture the sensor. So, so let's start with a simple model, because you will see that things get complicated very quickly, right? If you can solve, if you can derive some results with this simple model, then we have the option of elaborating on the model or generalizing, right? If you cannot solve the simple, if you cannot work on such simple model, then the problem becomes much more difficult. As I said, just to recap, X is the state, Y is sensor measurements, U is the control input, and these are process noise, which models uncertainty in the model, and BK is sensor noise, right? So what is nice about this is that a lot of the definitions and ideas and also results can be applied to general nonlinear time varying systems, right? So what doesn't work is the analysis, right? Once you generalize, you still can apply, and things do work actually quite well. Sometimes they work even better. Nonlinearities actually do help in, for instance, for detection. But what becomes difficult is to provide the generality of results that linear systems usually allow you to have. Okay, let me give you an example, right? And this is again an academic example. Take a discrete LTI's linear time invariant model, right? This is in discrete time model. And let's take a vehicle which is moving on one dimension, right? Just going back and forth, right? The state is velocity and position, right? And this is nothing but a glorified double integrator, which is discretized, right? And the inputs is a throttle, and the outputs is a subset of velocity and position. Defender strategy leverages information which can include previous outputs, previous control inputs, and model knowledge. Okay, so you define this information set, which says what does the defender know. Okay, and this is the knowledge. And we define an admissible defender strategy. Apologies for the thing that has moved, as a sequence of deterministic measurable functions, which takes the information and maps it to an action into the system. The actions can be, for instance, a control input time, or a change in the system configuration, the topology of the system, right? And in you define the set of all admissible strategies. In addition to acting on the system, the defender will perform tasks such as estimation and detection. An admissible detector, again, is a sequence of deterministic measurable functions, which take the information set and maps into a decision. For instance, one of the easiest decision to make is H0, the system is operating normally. H1, the system is faulty or under attack, right? It's not operating normally. Right? And you can use this for what we call passive detection. For instance, if you assume that the model is known, right, you have the system, right, that to inputs provides measurements, right? At the same time, and this is an algorithm that is running on your computer, you have a model of the system, right? And you take the very same input that is applied to the system and you inject into the model, and what you get is the expected outputs. Okay, then you compare measurements and expected outputs, right? And you can leverage all the existing detection theory, and you can test the two hypotheses. Am I operating normally or am I not? Right? Let me just give you some example. Right? Class of detectors is chi-square detectors, right? Where you leverage the estimator, right? Kalman filter is nothing an estimator that takes the measurements and then produces an estimate of the state, right? And what a chi-square detector does is, you guys are experts in system identification and fault, so it would be trivial. I apologize for that, but nonetheless, it lets me do this in a kind of a closed fashion, so that I don't have to. It's self-contained. You establish this difference, which is the difference between your sensor measurement and the expected sensor measurement. Okay, And what you do, you read your book on estimation and detection. Basically, you square the term, right? And you sum a number of these residues, you can call them, right, over a finite horizon. You square it and you weight it through some matrix, which is associated with the noise of the system. It has to do with this Kalman field, right? And then you design a threshold. The way you design a threshold, you set a desired false alarm rate, right? Of course, for all practical purposes, false alarm rate needs to be low, right? And because otherwise, we'll spend this. Very good question. In passive detection, how do you differentiate a failure and actual attack? You can't, right? Simply, you just detect an anomaly. You have to perform further intelligence on the system to be able to tell. So you design your threshold according to the desired, and then if your function goes above this threshold, then you determine that, again, to just go back to your question, you say there's an anomaly. You cannot conclusively say it's an attack, or whether things are operating normally, right? The problem with this is that it's called chi-square detector, because with linear systems and Gaussian noises, then the distribution is chi-square, so it's something that you cannot write in closed form, and therefore this probability of detection can only be computed, right, rather than written in closed form. Okay, so the attack model. So the framework can consider attackers with very general abilities, right? Denial of service attacks, as I said, topology attacks, integrity attacks, right? And for instance, right, you can have joint topology and integrity attacks, where the topology attack is one that modifies A, which is the dynamics of the system, with if you have a power system, maybe you bring down one distribution line or transmission line, right? And you can combine it with an integrity attack, where you change the sensor measurements, perhaps to hide the topology attack that you have perpetrated, right? And here in the smart grid, for instance, you change PMUs while destroying transmission line. Again, now the attacker strategy leverages the attacker information just symmetrically as the defender, right? And the information set is composed of its own inputs, right? How am I corrupting the system? Public inputs and outputs, right? What is it that I know about the system, right? The inputs and outputs, which might be available. And initial estimates of the model, right? The defender strategy, and the detector. Do I know what the model of the system is? What's the strategy of the defender, and what is the algorithm, right? In security, if you take the so-called Kerckhoffs principle, right, and you expand it to cyberphysical system, you would say that it is not a good practice to expect the system to be secure based on obfuscating the methods, like the strategies or the detector, right? It would be analogous to pretend that the system is safe just because the attacker does not know the method of encryption, right? Which is very poor security. So usually this good practice is to assume that the control strategies, detections are algorithms that the attacker will know. So you define also an admissible attack strategy as a sequence of deterministic measurable function, which takes the information set and maps into action, just symmetrically. And an integrity attack on sensors or control inputs, for instance, a change in the system configuration, right? Or a denial of service attack, right? Where UA is again the set of admissible attacks. Okay. So maybe this, so this is the setup of the problem, and maybe this is a good, yeah, it's a good time for to take a break. This just sets up the problem, and later on I will be delving into providing some examples of integrity attacks on systems, and show some limitation of passive detection, which will then motivate the need for active detection.
Thank you very much, Bruno. What time would you like to resume?
10 minutes, is that enough?
Okay.
So I have 33 past the hour here, so at 43 we can
Okay.
right? I'll be here if people have questions. We can also use the breaks for discussion. So you guys do whatever you want. I'll be here.
Thank you very much. So we resume in 10.
Yeah. Okay. Let's resume. All right. So far, I hope that I have motivated sufficiently the need for advancements in this area and how important it is. And honestly, more broadly than just CPS, looking at the number of attacks, right, and the increasing instability, I would say, in the world equilibria. I think this is more important than ever. So I think there's not going to be any dearth of investment in the field, both from governments and industry. Okay, so let me. This is what I would like to cover today and tomorrow. Of course, I will not be able to do all of this. Right. So we'll just stop where we get, but I'll be happy to share all the slides nonetheless, so that if you're curious, you can just skim through, and then if you have questions, you can go and look in the literature. You can contact me, and right, and we can talk about things. And if you're curious about something or advancing, I'm always happy to work with people. So let me start from detection, right, and passive detection. And this is for the purpose of showing how difficult problem can become when you start introducing into our system theory, right, the notion of an attacker, right? If we look at the history, right, we have always designed system with the assumption that all the actors are benign, right? And therefore we always try to maximize performance and leaving some of our basic algorithms very brittle and very susceptible to attacks, right? And so let me show you in a very, very simple example. Right? It's a paper that we wrote many years ago with my students, with Joao, España, and at the time Kyriakos was a postdoc with Joao, while my student Yilinmo is now back at Tsinghua University in China. So let's say we want to decide whether the state, right, is 1 or -1, right? Could be operating normally or being under attack or being, right? It's just a binary detection, right? Where you have a prior, right? Where P- is the prior probability that the state is -1 and P+ that it's +1, right? And you're measuring the system through M sensors, right? You set up the probabilities that yi's are in a set S, given that the state is -1, or mu y is the conditional probability that y is into a certain set, given that x is equal to 1, right? The yi's are conditionally independent of each other. So you define this product measure, mu and nu, as shown here in the equation, right? Then you define the log likelihood ratio of the ith measurements. Okay, that's very standard. Now, a detector is a function that goes from the set of outputs Rm into 1 or -1. And with this setup, the optimal detector is with minimum detection error is the naive Bayesian detector, right? Where x is estimated to be -1 if the sum of the log likelihoods is below the log of P- over P plus, or vice versa, right? You notice very quickly that one corrupted measurement can change the detection result, right? So the algorithm, one of the most famous algorithm, as it is not very secure. Okay. So let's define the attack model. Right? We assume that the attacker knows the following, right? The detection algorithm, right? This is again according to Kerckhoffs's principle, right? You always you cannot assume that you can obfuscate now the algorithm, right? The attacker will come and go. He knows the true state. This might be a unreasonable assumption, but it makes the attacker stronger. So all the results will work, even if the attacker does not know that. And all the measurements. It's a fairly powerful attacker, right? And the attacker can manipulate up to L measurements arbitrarily, L of the M. Where gamma is a vector, right? Where gamma i's are 0 or 1, basically they're 1 in correspondence of the measurements that are corrupted, right? And you have at most L corrupted measurements. That's what this equation is saying. The attacker wants to maximize the probability of error, okay, by wise use of deciding which measurements to attack and how to corrupt these measurements. So this is a pretty powerful attacker, if you want to put it in. So it knows state, the detector, it can read the sensors and violate the subset of sensors. So it's fairly powerful. It's not the covered because there are a number of sensors that cannot be corrupted, right? If you could corrupt all the sensors, there would be basically nothing that we could do. Okay, the optimal strategy for the attacker is the following. If is move if x is -1, right, and the detector would do the right thing, right? The measurements is in the space where it would actually give you a -1, then it will corrupt the measurement in such a way that they would move to the set of measurements where the result would be 1, right? If you're already if the detector is getting it wrong, then it would do nothing, right? Trivially. So we're going to partition the space of measurements, right? And there are 3 categories of points in Rn. Right? So if for some attacks, f can be 1, and for some attacks, f can be -1, and this is bad, right? Because the attacker can move. And then the other 2 is for all, and the other is that whatever the attacker is doing, the detection doesn't change one way or another. Okay. For instance, right, if you're in the first case, right, the way it's partitioned, and the attacker can always decide the outcome of the detection, while in the second case he cannot. Okay, which is a good. So we define the worst case probability of error, right? So we define these sets, right? It's the set of measurements such that the result of the detector will say -1 regardless of the attack, and y plus is the set of measurements for which the result of the detection will be 1 regardless of what the attacker does. Okay, and the detector can correctly detect x if and only if, right, xy belongs to one of the 2 sets, right? Which means that the result is -1 and the observation belongs to y minus, or the detector is the detection is +1. I mean the event is +1 and the observation belongs to y plus. In this case, the attacker cannot do anything, right? If you define this way, then the worst case probability of error is written below. Now, it is clear that there's some monotonicity here, right? If you have 2 detectors, F and G, right, and y minus of F is contained y minus of G, and y plus of F is contained in y plus of G, then the detector G is better than the detector F, right? So the performance of the detector depends on how large these sets are, the good sets are, okay? Okay, so let's take a look for different detector, right? For this detector in E, right, Y plus and Y minus are the empty sets, right? So the probability of error will be 1 because the attacker can always move. For the second detector, right, and here we're assuming that we are corrupting one measurement, right? The Y minus is the bottom left quadrant, right? If you're there, there's nothing that the attacker can do by corrupting one measurement, right? In order to make the decision wrong. Okay, just as an example. So what we were going to define is a Hamming-like distance, and the trade-off between Y plus and Y minus. So you'll define a metric, right, which takes two measurements and computes the Hamming distance between these two measurements. Right, it's not really a distance. So, and you let then Y1 and Y2 be two subsets of Rm, right? And you define the distance between these two sets as the minimum distance, the minimum over Y1 and Y2, right, of the Hamming distance between Y1 and Y2. Okay. And if you want to define the distance between an element and a set, you just consider that element a set itself. Okay. So first of all, so ideally, you would want Y plus union Y minus to be the entire space, Rm. Right? If you can do that, then you're in business, because an attacker can never corrupt. Right? Unfortunately, you can prove that for any detector, the distance between the two sets, Y minus and Y plus, is always greater than 2L plus 1, where L is the number of corrupted measurements. Right? So you cannot bring them arbitrarily close. You cannot cover the space, in other words, as expected. Okay. So the other lemma is that given two sets, X minus X plus, two subsets of Rm, and given the distance between these two sets as a constraint to be 2L plus 1, there exists a detector, okay, such that X minus is contained in Y minus of F, and Y plus in Y plus of F, right? This is an existence result. Okay. Now the theorem says the optimal detector is of the following form. Is F star of Y is equal to 1 if the distance between the observation and Y minus is greater than the distance between the observation and Y plus, and minus 1 vice versa, right? So you take the measurements and see whether it's closer to the set X minus or the set X plus, and then you decide based on that, okay? And where X plus and X minus are the solutions of the following optimization of this optimization problem, right? Where you design these sets as to minimize the probability of error subject to the constraint that you have to enforce. Okay, so as you can see, this is a very tough optimization problem to solve because it's over sets and they're not even parameterized. Okay, but that's how we define the design of the optimal filter. Okay, so this is the structure of the optimal detector as we have seen, right? define these sets, and if y is closer to x minus, then it's the result is -1. If it's closer to x plus, the result is +1, and these have to be far. And then what you need to do is just build a detector that maximizes this the size of these sets. Okay, okay. So these are some of the results, right? Of course, I cannot solve this optimization problem, but I can provide you these results, right? And this depends upon the number, the relative number, the number of corrupted measurements relative to the number of sensors. Okay. If M is less than 2L, right? Then basically this is saying that more than half or more, or the measurements are compromised. Then there is nothing that you can do, right? You basically decide based on the prior knowledge. That means that basically corrupting half of the measurements is sufficient to render the detector useless, or all the measurements useless. Right. Which is interesting, right? And this is reminiscent of error correction coding. If you look at the results, right? So what this is saying is, for an attacker, is that I don't need to corrupt all the measurements. I just need to corrupt half of them. Then and then the detector has to throw away all of them, because that's the best thing to do, right? If M, right, is equal to 2L plus 1, right, precisely, right, so that I have one measurement. So if I separate the number of sensor good and bad, I have one more good than bad. Then the optimal detector is actually based on voting, right? So it's distributed in a certain sense, where each detector computes M individual estimate by Neiman-Pearson detector based on the individual measurements. So so you basically compute n different detectors based on the m different detectors based on the m measurements, right? And then you decide based on voting, right? You decide that it's 1 if there are more than half of xi being 1. Otherwise, it decides -1, which is very interesting, right? In this very specific case. In the case, which is the most interesting case, where actually you have less than half of the measurements that are corrupted, then it's difficult to compute the general detector, right? And so we propose a heuristic detector. So where basically it does the following: you order all the log likelihoods, right, in descending order, right? And so you throw away L measurements with the largest log likelihoods, right, and the L measurements with the least log likelihoods. And then the detector sums the remaining log likelihoods, right, which are m minus 2L, which is greater than 0 given our original condition, and compares the sum to the log likelihood, right? You choose 1 if the truncated sum is, you choose -1 if the truncated sum is less, right? It's a usual division rule, right? Otherwise, the detector chooses x hat equal to 1, okay? And what you can prove is this heuristic detector is asymptotically optimal if the measurements are identically distributed. So what this is saying is as the ratio of good to bad goes to infinity, right? Then this is the best way to proceed, and this is reminiscent of robust detection, right? To draw a let me draw a parallel, right? Let's say that you are going on TripAdvisor. You're looking for a hotel, right? And there are M reviews, but you suspect that L of these reviews are given either by friends of the proprietor of the business or by competitors, right? So what you're going to do is throw away the best L reviews and the worst L reviews and decide based on the rest, which are the least informative reviews to a certain extent, right? That's the analogy that you can draw, right? And it's a heuristic, but it's optimal as, again, the ratio goes to bad goes to infinity. It's pretty interesting, right? I can show you a numerical example, right, where you have non-informative prior, it's 0.5, and you have three measurements with 0 mean and variance 1, right? And you look at the probability of error versus the number of sensors. This is how it decays. Right? Okay, so just to wrap this, right? So we consider the problem a very simple problem of binary detection, right? And as soon as you put an attacker model, the simple result, the one that has been in the books for decades now, is not valid anymore, right? Because in theory, just one measurement could corrupt the entire decision, right? So we provided the optimal attack strategy and defined the static detection, and we obtained the structure of the optimal detector, right? And although the way we pose the problem leads to a very difficult optimization problem, we had closed form optimal detectors in the case where more than half or more are corrupted, or whether there is the number of good sensors is one more than the bad sensors. And also we provide a heuristic for the case where less than half of the sensors are compromised, right? And I think my former student Yilinmo has advanced this problem, so you might want to look in one of his papers if you're looking at future work on. I have actually stopped here. Actually, we had another version of this, which is slightly different with Joao, where we looked at the game theoretic counterpart of it. This is more of the robust, the robust version of it, right? And it's not posed as a game. Okay, that's all that I want to say on this. Any question? If not, then your question, again, feel free to ask, is the characterization of stealthy attacks, stealthy false data injection attacks in particular. Right? And this is just to, again, this realm of passive detection and highlighting what are the capabilities of passive detections and also the fundamental limitation of passive detection in the presence of attacks. Okay. Let me give you another example. Okay. Consider a control system monitoring this linear time invariant system. The system is, again, posed the usual discrete time LTI, where, again, X is the state, Y is the measurements, and U are the control inputs. And let's assume that all the measurements are, and the initial conditions are Gaussian, right? This is the usual assumption that you make, because then you preserve Gaussianity of the state, and Gaussianity, as you know by now, it's a nice property to have, because a linear function of a Gaussian is a Gaussian. And, right, and you can invoke central limit theorems and to say the Gaussian is always good. Okay, so let's equip our system with 3 algorithms. One is an estimator, which in this case is a Kalman filter, which it happens to be optimal just because of our choice of the model. Let's equip it with a control system, right? And we can choose whatever we want, but given that we have this beautiful LTI Gaussian system, we'll use LQG, right? Which is the linear quadratic Gaussian, right? And for people who don't know what this is, it's an optimal control scheme that aims at minimizing the expectation of this cost. And this cost penalizes, right? It's a squared, it's made, the elements are the squared, weighted square of the state and weighted square of the input. Basically, I want to regulate the system around 0, right? Anything that, as soon as I go away from 0, then I incur some penalty. But I want to do it. I want to do it by using the least energy, the least amount of control effort. Okay, that's what the LQG does, right? So, and the name of the game is to find the U that minimizes this cost. And it is a very old problem. It's basically a dynamic programming problem that, thankfully to the fact that we are in this beautiful linear and Gaussian, can be solved in closed form, and the optimal input is this fixed gain controller, right? Where S is the result of this algebraic Riccati equation. Okay, the innovation of the Kalman filter, right, which is that quantity that you remember, right, is IID Gaussian distributed with zero mean. And when you square it and you build a detector, you get a chi-square detector, right? So you take this innovation or residue, or however you want to call it, you square it, and you weight it with the inverse of the covariance matrix of the estimator, right? And you set your desired threshold. Now, again, like like we've done before, you have to define the attack model. Okay, the attacker knows, so the information set knows the matrices A, C, and also knows the Kalman gain, so he knows how the estimator works. And the attacker can also control the readings of a subset of the sensors. So the measurements received by the Kalman filter can be written in this form, right? Where YKA is the bias introduced by the attacker, and as I said before, gamma is a diagonal matrix where the gamma i's are 0 in correspondence of the sensor measurements that cannot be corrupted, and it's 1 where the sensor measurements can be corrupted. All right, you assume that the attack begins at time 0. You also assume that the attacker chooses strategy before, right? So you will gain independence between the WK, VK, and the YKA. Right. So if you want to again place it right here, he has knowledge of the system, and disruption resources are limited, right? While disclosure resources are pretty large. So it's a pretty powerful attack again. So it knows the state, the detector, can read all the sensors, but it can only violate a subset of the sensors, right? If we violate all of them, then we'll be in the covert attack. So this is a false data injection, right? So on sensors, right? And okay, so this is the system diagram. Not very revealing, right? Where the only thing I would highlight is that the corruption occurs here, where the sensor measurements are corrupted by the attacker, right? Who might then insert also its own input, but that's irrelevant for now for us, right? So this is the healthy system, and this is the compromised system. It's compromised because of this perturbation in the measurements. Okay, so one way of analyzing this is to compute the dynamics of the difference between the compromised and the healthy system, right? And if you compute this, given this independence assumption that we stated, you can actually show that the expectation of the corrupted state is delta x, and the covariance is the same. And you can make similar statements for all the other variables involved, right? So, which means that in order to characterize the performance of the system under false data injection attack, we only need to focus on the delta system. Okay, let's define this alpha feasibility. We'll say that the attacker, the sequence of attacker inputs, right, from 0 to n, is called alpha feasible. Right? If during the attack the delta z, right, which we have defined, it's basically the innovation on the delta system. The distance between the corrupted system and non-corrupted system, which is equal to this, is less than alpha, right? Where this is the KL distance between Z prime and ZK. So what this says, it's called alpha feasible, says that if alpha is your desired threshold, right, as long as your threshold is below alpha or below, then you're not going to get detected. Right. Is above, sorry. So if alpha goes to 0, then the compromised system and the healthy system are indistinguishable by the chi-square detector. So, so under these requirements, the action of the attacker can be formulated as a constrained control problem, where in this case, YKA is the input from the attacker. The input of the attacker is YKA, right? And you basically design this YKA so that this constraint is satisfied. And that's why it's a constraint control problem. So to characterize the robustness, again, of the control system, we need to compute the reachable region, Rk, of delta xk. Delta xk is basically the perturbation that the attacker can induce into the system by modifying through this YKA, right? And if you collect all the different states that can be reached through this corruption, then we define the reachable region Rk, right? It's the perturbation set, basically, right? Which can be, that will be reached, and he has to satisfy this this constraint so as to remain stealthy. And so what we'll do, we'll focus on finding a necessary and, oh, I have a question. Why is the state affected in the corrupted system if the attacker? Oh, it's affected through the estimate. That's how it's affected, right? Because the estimate will use the corrupted measurements. Basically, here the name of the game here is to induce the system to make the wrong decisions. Okay. So here, so we'll find necessary and sufficient conditions under which the union of all the Rk is unbounded, right? Which says, can we find conditions such that I introduce a perturbation on the measurements, which has to be small enough as not to induce detection. If I change arbitrarily the y's, I will incur detection because the delta zk will be large. Okay, but can I find small perturbations in the measurements that actually will lead me to send this to arbitrarily pull the system away from my desired state, which is 0, for instance, in our LQG. Right? When I first posed this problem, the natural answer was, the intuitive answer for me was no, you can't do it, right? Because small linearity would tell me that small perturbation in the input produce small perturbation in the output. And that's why I thought that this could not be possible. In reality, if you exploit observability or lack thereof in a certain case, it's something that you can do, right? And this is the theorem that says it, right? So the union of the Rk, right, which is basically the reachable set by the attacker, is unbounded. Let's see what time it is. If and only if A has an unstable eigenvalue, and the corresponding eigenvector satisfies the following properties. CV has to be in the span of gamma. Remember, gamma is the matrix that tells us which measurements are compromised, right? So the span of gamma is the column space of gamma. And V is in the reachable space of this pair, which is the is the controllable set for the attacker, in other words, right? It's controllability of the attacker. So basically what this is saying is that if I have an unstable eigenvalue, then I can reach the unstable eigenvector, right? And if this is hidden from the controller, right, it's in the span of gamma, right? Which means that it's rendered, that direction is rendered unobservable via the attack, then the system will be unbounded, right? Basically, I bring the system to the unstable direction, and I just let it go unstable by itself while hiding it from right? So this aside, so first of all, this is an if and only if. So this is only true if these conditions are satisfied, right? In other words, if the system is stable, there's nothing you can do. So my intuition of the linearity could not allow that holds, right? But also, what's interesting about it is that it provides some instructions for both the attacker and the defender. Unfortunately, also for the attacker, right? So, so for instance, right, if you want to check the robustness, this is not resilience. That's one of the mistakes that I made. One can find the unstable eigenvector of A and compute CV, right? If this CV is sparse, that means that the attacker only needs to compromise a few sensors to launch the attack. So if it's sparse, I know that there's a few, and by computing this, I also know which sensors are crucial to protect, right? And once I know that, then I can, if I have thousands of sensors, let's say, right, I can probably prioritize security investment by protecting better the sensors that are more crucial, right, or add redundancy. So, good. Oh, okay, Chris. Bye, Chris. Take care. Okay. So basically, you can add the more redundant sensor. Anyway, so it is a very algebraic theorem, but it contains design cues, unfortunately, for both the attacker and the defender. That's what I like about this result, and that's why I'm sharing it with you. Let me give you an illustrative example, right? So this has been published in some papers, definitely control papers, in the CDC paper and some TAC paper. Okay, we can talk about this, Michelangelo, later on. So in this case, yes, you're right. So let's go back to our vehicle that was moving along the x-axis, right? Right, our one-dimensional world, like a train going on rails, right? And this is our glorified double integrator, right? It's the dynamics where x dot is velocity and x is the position, right? And you measure both velocity and position with some error, right? And you make things simpler because this is an academic example. So you design your Kalman gain and control gain, right? So the question for you is the following, right? So if you were the attacker here and you were to corrupt the measurement, right? Which one would you could only corrupt one. Which one would you choose? Okay, let's take a poll. And how should we do this? Okay, we'll do it this way. Let me take a look at the participants. So if you, let's see what the choices are. Hold on one second, then indulge reaction, kind of reaction. Okay, so if you want to corrupt the velocity measurement, then put the thumbs up. If you want to corrupt the position measurement, then just clap your hand, or yeah, or clap your hand. Okay, let's take a look at the poll. Don't look at that. Okay, all right, are you voting? What can I see? how can I participants? Oh, there. Okay. All right. All right. If you don't know, just if you've done it, do it again. Okay. As I said, if you're voting for the velocity sensor, thumbs up. If you're voting for the position sensor, clap hands. And sorry, I should have set up a poll. Okay. Well, actually, I couldn't. I'm not. Okay. Velocity. I get a couple of velocities. Okay. This is the answer that I always get. It's the velocity sensor. Right? Nobody is voted for the position. All the others are asleep, or I hope that you're sitting at the beach somewhere, ignoring me. Okay. All right. And to be honest with you, whenever I take this poll, I realize two things. One, nobody reads my papers, but that's okay. That's a common feat. I'm okay with that. Or very few people do. The other thing is that this analysis that we just did has value, right? Because it's very counterintuitive, I guess. So here it's easy to check that the unstable eigenvalue is this one. And being this one, if the position sensor is compromised, then the conditions of that theorem are satisfied. And you could push the state xk to infinity, right? So the right sensor to corrupt is the position sensor. The velocity sensor is compromised, then the researchable set is bounded. And the intuition is that, you know, small perturbation in y produces small perturbation also in the state, right? And you can actually show that, right? If the position sensor is compromised, right, basically you see that delta x can grow arbitrarily, right? And here you can see that your alpha is 1, right? For linearity, it can be whatever you want, right? And then you can go to infinity, right? And if you do some, if the velocity sensor is compromised, then the reachable region R cannot grow unbounded, because otherwise it violates the constraint, right? And this is just an ellipsoidal approximation where you have just the blue are upper bounds and the reds are lower bounds, right? And we simulated for a number, right? And basically the reachable set is somewhere between the outside of the lower bound and inside the upper bound. Okay. So analysis helps. Right. I have an application that we did back at I was at Carnegie Mellon on electricity market pricing, where basically you can. I don't want to go into this because just it will take too long. But basically, if you know how nodal price is computed, it depends upon the how congested are the transmission lines, right? And if there's no congestion, then the price is all the same. If they are congested, then the price varies. So you can use this this scheme, even the static version of it, not the dynamic version of it, where you basically you buy and sell virtual power the day before, and then you corrupt the measurement in such a way that the pricing will come in a way that will be compatible with your buying and selling strategy, and you will make money off of it, right? And mathematically is the same thing. Right? You just pose it as an optimization problem, where the delta PGI is the corruption that you induce, and down here are the constraints, right? And I mean, this just takes too long, right? And what I'll show you is, so the strategy, the attacker just first buy and sell at the day ahead market at locations J1 and J2 with certain prices, right? You can assume without loss of generality that one price is higher than the other. Then when the price gets realized, you change the measurements in such a way that nothing looks congested, so that the prices are you manipulate the state estimation to ensure that lambda 1 is greater than lambda 2, and then you can measure the profit that you make. And so by following this strategy, we actually simulated this on the 14 bus, the IEEE 14 bus examples, and you'll see how you buy and without buying and selling, with no attack, nodal price will be different. Instead, with the attack, you enforce that they're same, and since you bought and sold at different prices, then you make money. Okay, that's all. Anyway, so if you're curious about this, we published a paper. At the end of the lectures, and in the slides, I will put I'll put references. So this was published in, I think, the first issue of the IEEE Transactional Smart Grids and maybe Smart Grid.com. So you can read that paper. Actually, it has been read quite a bit. Okay, so just to conclude this section, right? Consider this false data injection attack on sensors, right? So first you define the attack model, right? You can formulate the action of the attacker as a constraint control problem, right? And you analyze the performance of the estimation control algorithm in the presence of this compromised sensors by computing this reachable set, right? You obtain necessary sufficient conditions, algebraic conditions, characterized when an attacker can actually destabilize the system. And this provides design criterion. Of course, these are designed at design time, right? To improve the resilience of the control system against this kind of attacks by identifying what are the critical, if any, the critical sensors to protect. Okay. I feel a little bit out of steam. Okay, let me. So this can be extended to false data injections, both on sensors and actuators, right? And I'm actually going to skip this. It's just an extension. I don't think it's very revealing. And perhaps move to something that might be more of interest. It will be left in the slides if you're interested. Okay, is there any question? This point. How do people feel? Tired? Huh?
I think it's some good material that you are presenting. Yeah, I don't know how others feel, but I find it very interesting.
Okay, thank you, Stelios. Do you think is a good place to stop? I don't.
Yeah,
I
I leave it up to you. I mean, we have some more time. I don't know if you have something else to say for today.
I mean, ideally, which is something that I can speak for for quite a few hours, which I'm not sure is the right thing to do. But ideally, I would like to have a little bit, maybe 5 minutes of discussion with people, which you don't have to feel like you have to ask questions, technical questions. It can be just a more general discussion.
Yeah. Always with the online events, it's a little bit more difficult, and it's always a challenge to make people respond.
Yeah, and I get zero feedback. So that's one of the issues. Okay, then let me just give you a okay, let me just make some remarks. Okay, I think, right, there is value. What I wanted to convey is that there is value by enhancing models of dynamical models of systems, right? With by introducing the notion of an attack model. Right? First of all, as you can see, results that are 78 years old become new, right? So there was, and I think there still is, a very good chance of providing fundamental results, right? Which is otherwise very difficult these days, at least in the area of systems and control, right? A lot of very smart people have worked in a number on problems of control, right? And in great depth, which means that the problems, right? All the low-hanging fruits have been harvested, and what is left are really hard problems, or problems nobody cares about. You don't want to be in either situation, right? So that's from just an intellectual perspective. From a practical perspective, right? We live in a world where we have no choice but to cope with the notion of an adversary being present, right, and aiming at disrupting our designs. Okay, so I think that we will make our designs all the most relevant, right, if in addition to what we have tried to do in the history of the field, which is drive performance, right, in our objective, we also introduce the notion of security. Okay. I think there is from a market perspective, which is something that is difficult, right? Because as you will see later on or tomorrow, right? In order to overcome fundamental limitations, right? In, for instance, detection, you will have to introduce active schemes. When you introduce active schemes, then you're trading off necessarily performance and security, right? So cost will be added when you're undeniably and inevitably cost will be will rise when you're looking not just at performance but also at security, right? And if we follow the trend that security was added afterwards because nobody wanted to pay for it at first, then this will be a problem, right? My sense is that especially in physical systems, the risk, right, of deploying systems, and I'm referring just to two infrastructures, right, transportation and power. Deploying systems which are susceptible to attacks is just too dangerous, right? And therefore we don't want to take the chance. And I hope that through a combination of regulation, and by regulation I mean clear rules that regulate liability, right? Once you start defining who's liable for a security breach, right? Liability carries a cost. Then companies can justify, right? Can do risk management, risk analysis, and risk management, and therefore justify to their budgets the investments in security. The problem is systemic because systems today are born out of system integration of parts which are developed by different entities, right? So when, and this is a very interesting problem in itself, right? How do you design a system? It's a game theoretic problem, right? A system where, it's a mechanism design problem, right? Where all the agents that contribute to building a systems have common, their utility functions, their common objectives to achieving security. Because as you know, a system is as secure as the weakest of its components. That's one interesting direction. The other is compositionality, right? How do you compose tools and security properties in such a way that you can preserve security, right? If I take this component and I secure it, and I take this component and I secure it, are there any rules that guarantee that by combining them, then the overall system is secure? Compositionality is very hard to establish in security and systems, and I think that's another very, very interesting direction. So these are some thoughts which are more general and transcend from the technicalities that I went over in here. But what I wanted to really motivate is that there is a need, right? That it's intellectually stimulating, and that therefore I think it's a field that is still fairly open, I would say, especially when you start, because the security, although we talk about CPS security, it's either cybersecurity or system theoretic, but the two have not been brought together. Made some timid attempt to try to unify using notions of information flow. I'm not sure that I'll have time to talk about it but I haven't made much progress on that regard. The other thing is passive detection as limitations. We have seen it in the very simple example of binary detection, right? And we have seen it in the case of false data injection, right? Where there are cases where there's not much that you can do. Right? So tomorrow we will start from here, right? From this observation, we'll introduce a number of active detection techniques where you use control, not just to control a system, but also be able to detect and identify corrupted components, right? And we'll do it, we'll look at a couple of different techniques of active detection, which I call physical watermarking and moving target. All right. Well, I thank the 30 of you who are left for enduring with me. I certainly, it is not my preference to speak uninterrupted for 2.5 hours. And so I hope that we can have more discussion tomorrow. But thanks again for your attention.
Thank you very much, Bruno. Thank you very much for accepting the invitation to give us this today course. One practical question that I have is with respect to the starting time for tomorrow.
Yes, 8 is okay.
Okay. So as it was scheduled today, so our time is 4 p.m., 4 in the afternoon.
Yeah, I mean, I actually, in the invitation, now I see 8 a.m. for tomorrow, but for today, the invitation was from, I think, 2 a.m. and onward, so I could not tell that it was actually 8.
Thank you very much.
All right.
Actually, I have one question. I was thinking about this, the landscape of autonomous vehicles.
Yes.
And nowadays, there is a lot of research also on cooperative autonomous vehicles and how you can coordinate vehicles to pass intersection without stopping and these kind of things. And I'm always very curious, I mean, about the security aspects of these things and whether they can work in practice and still, I mean, take into consideration, let's say, the security aspect and to a certain extent be robust. I don't know if you have done any research on this, or because you have mentioned the transportation section.
I'll give you tomorrow one example of for platooning, which has to do with platooning. But the problem, both intellectually and technologically, is open, very open, right? Unfortunately, as I remarked a few times, when companies have to bring things to market, they don't think about security, right? If you look at right now, the mantra for autonomous vehicles is V2X, right? Vehicle to vehicle or vehicle to infrastructure, right? And this technology called dedicated short-range communication, also called DSRC, had emerged, right? There are radios, right? The security properties of these protocols are terrible, by the way. So these are not good premises, right? To start with, right? It looks like maybe 5G is emerging as an alternative to it with these roadside units. So it is very open. It's actually not clear how this is going to be implemented yet. And it's a formidable challenge and actually a worthy one in my mind. Because because of the danger of the problem, right? You corrupt one car, you have corrupted a line of cars because they all run the same software, right? So you have pretty much an army at your disposal instantly, and that becomes so prevention is key here, I would say, and then right, the trade-off between here performance and security is really evident, right? Because the closer you push cars together, or the faster, right, then the more dangerous from a security standpoint things are, because you know, it's easier for an attacker to induce, right, to induce damage rather than keeping cars meters and meters apart. So it's a really well defined problem, although not intellectually and even less technological. Just to tell you, and you know, there are a number of companies that have received billions, literally billions of funding for autonomous driving, right? Aurora and the likes. And the CEO of Aurora, Chris Urmson, who's actually is one of the first engineers who worked at CMU on autonomous driving, gave a talk here at WashU a couple of years ago, and I asked him about security, and he was very quick to dismiss the question, saying, "Yeah, we'll think about it." That's what he said, which worries me a little bit.
Okay. Thank you very much, Professor Sinopoli. Thank you very much, everyone, for attending, and we look forward to your talk tomorrow.
All right. You guys have a good rest of the day. Take care.
Have a nice day as well.
Bye-bye.
Bye-bye. Thank you.